All right, so guys, grab the assignment that we did last time, grab this activity, and I actually have a question for you that's going to lead into what we're doing today. So guys, if you remember where this activity came from, literally looking at page 1 of the activity with me, just start right here. Guys, literally just helping you sort of see the connections. Guys, what we did is we took this activity and we went back to assignment number 3 and assignment number 4. And what we did is we lifted some of the Lewis dot structures out of 3. We lifted some of the Lewis dot structures out of assignment number 4. We drew all of those Lewis dot structures all throughout this assignment. So guys, the hope was that you didn't have to draw any of these Lewis dot structures from scratch because you already had them, right, in assignments 3 and 4. Then guys, what you did is you grabbed a Chromebook and you opened up that FED activity and you drew as best you could, but you drew what these things actually look like. Guys, I have an advantage over you because I could screen capture them. You didn't have that advantage. You actually had to hand draw them, and then off to the right, we wrote out their common names. So guys, that's where we should be right now. Are we all settled and okay with that? Okay, so guys, again, you are not going to turn these in today. You're actually going to turn them in on Monday. So the question then becomes, if I'm not going to take these from you today, what are we going to do with them? And guys, the answer is this. Did I grab the right? It doesn't matter. Oh, wait, I'm on slide 0. I'm in the last slide rather than the first slide. For some reason, oh no. I think my computer just totally died. Say a prayer. Moment of silence. Come on, little fella. Oh, wait. Maybe I resurrected it. Hold on. The lovely bit is that all of this is now in the screencast, but that's how we roll. Guys, I don't know why this opened up to the last slide rather than the first slide, so let me start over. All right, here we go. Here's the first slide. So again, guys, the idea is that we had the Lewis dot structures, and then what we did from there is we figured out what they look like kind of three-dimensionally. So guys, this is what we're going to do today. All of these three-dimensional structures that you drew in your activity, guys, all of these have names. All of these have representative angles. And so, guys, what we're going to do today is this. We're going to figure out that these Lewis dot structures, they're valuable. They tell us bonding. They tell us bond order. But, guys, what they don't tell us is three-dimensional structures. So let me give you a little bit of a taste for this. So, guys, for example, CH4. We know that its Lewis dot structure is this. We know that these kind of look like 90-degree angles, but guys, there's not. There is not a single 90-degree angle in any of these molecules. So what you're going to find out today is that this is actually in three-dimensional space looking like this, and you're going to find out in about 10 minutes that this has a name. It's called tetrahedral. And you're also going to find out that these angles are not 90-degree angles, they're 109.5 degree angles. So now you're thinking to yourself, how on earth am I going to take these Lewis dot structures and how am I going to tie them to what they actually look like in space without the thing that we got off the Chromebooks? And guys, the answer is right here. Grab this class sheet that I gave you and let's talk. So guys, you know that we are learning throughout the year to think scientifically. And guys, when we think scientifically, we look for patterns, we look for structures, we look for organization. So guys, looking at the front of this paper, the front, guys, what are the things that your eye falls to that tells you about organization, tells you about patterns? Guys, chat with the person next to you. What do you see that speaks to your eye about patterns? Organization. You're going to be talking with each other a lot today, guys, so. So guys, let's take a look. And I know that some of you utilize these things when you write, but when Miss Collin and I put this together, what did we do to bring your eye to the way that this is organized? Guys, we bolded the major topics down the left-hand side. So as your eye falls to this, how many major topics are we going to talk about to begin the day? 4, right? We're going to, oh, sorry, this got drilled. This says electron domains. Then, guys, down here, we're going to talk about what we call Vesper Theory. And then, guys, finally, down here at the bottom, we're going to talk about bonding and non-bonding domains. Those actually kind of go together, you'll see. But, guys, we've got 4 big ideas that are all foundational. Does that sort of click in your head? Okay, now, guys, flip it over. Now, guys, again, we've got organization and we've got patterns. So, guys, chat with the person next to you about the organizational structure and the patterns on the back of this. What do you see? Guys, you got about 5 more seconds. Calvin, you're a genius. Say it again. What did you notice?
They're separated into tables.
Good for you. Guys, the minute your eye sees a column and a table, tables and columns, your brain is going, okay, we are going to learn similar information about different things. What's the information we're going to learn? Those are the columns. How do you know there's different things? Because there's multiple rows. And so, guys, your eye should fall to this and go, okay, I get a sense of how this is going to be structured as we move forward. But guys, did you notice the pattern as you move top to bottom down the page? Did you see it? Guys, read this stuff in bold. What's the pattern? How does it change as you go from top to bottom? What's at the top? 4 domains. What's below that? 3 domains. Below that, 2 domains. So guys, what you're going to see today is as we move from top to bottom, we are going to be talking about molecules with a decreasing number of domains. But guys, at that point, we've got a big problem, right? We don't know what domains are. But if you turn the paper over, guess what's the very first thing we're going to talk about? So guys, that's what we're going to do. So here's the way the day is going to proceed. We are going to first identify what domains are and make sure that you know how to work with them. Then guys, after that, we're going to talk about what they do to each other. Then after that, we're going to talk about what they look like. That's the entire first page. Then we're going to flip this over and we're going to get thinking about how they get organized in molecules, going 4 domains, 3 domains, 2 domains. Do you see the big idea? Then guys, let's get to work. Electron domains. So you've already got this in your notes. You're just filling in the blanks, but the idea is this. Guys, imagine that you go out on the prairie and you are in the domain of antelope. And antelope live in the prairie. And so guys, you get out there and you're like, okay, I am now in the domain of antelope. Guess what you're going to see out there? Antelope. And guys, it doesn't matter if you see 1 or if you see 1,000, you are still in the domain of antelope because domains are where things hang out. So guys, ready? This is a stretch. What's an electron domain? It's the place you find electrons. So guys, these electron domains are the regions where we find electrons around a central atom. And you're going, wait, didn't we call those orbitals? Well, guys, there's a missing piece here that we're not going to talk about. Orbitals turn into domains before they bond. And guys, we're not going to talk about it in here. We do a really interesting 2-day series on this in AP. But guys, in here, don't worry about it. If you're confused and you're going, wait, don't electrons hang out in all these pretty orbitals? Yes, but they turn into domains before they bond. We're not going to dig into it until you come back next year. So guys, the idea here then is that domains are the spaces where electrons hang out around a central atom. Now there's two kinds. The first is what we call bonding domains, and these are any type of bond. Could be a single bond, double bond, triple bond, does not matter. These are electron domains. In the same way that it doesn't matter how many antelope you see out in the field, it's still a domain, because it doesn't matter how many electrons, still a domain. Then there's another kind of domain, and these are the non-bonding domains, and these are just the lone pairs. All right, so guys, what have you got to be able to do with this? Well, before we answer that question, totally up to you. There's room for this in your notes. If you want to draw it, you can. If you don't, that's fine. But guys, the big idea is this. A lone pair of electrons is one domain. A single bond is one domain. A double bond is not two domains, it's one domain. And a triple bond, you guys, is also one domain. So guys, the question then becomes this. What do you need to be able to do with this information? So guys, let me show you. Well, first of all, questions or thoughts? You okay? Okay. So guys, don't write this down, but this is what you've got to be able to do with this. You are going to be drawing Lewis dot structures. And guys, please remember, this is the molecule that you have to memorize. By the way, we should talk. So today, Thursday, we're going to talk 3 dimensions. On Monday, I'm going to hand you model kits, and you're going to build a bunch of these molecules. And then, guys, next Wednesday is the test. So with that in mind, guys, we've already written the test, and this is one of the Lewis dot structures that you need to be able to draw. And remember, this is the only one you had to memorize. So make sure that's on your study list. So guys, what you've got to be able to do is this. For example, turn your eye to this carbon right here. And guys, please talk to the person next to you about how many domains are on that carbon. Chat about it. How many domains are on that carbon? If you don't agree, talk about why you're different. But guys, chat about it. Got just a couple seconds left. All right, guys, let's pull it together. Maddox, you're good at thinking through stuff. I love listening to you reason. So, guys, let's do this. Single bond is a domain, double bond is a domain, triple bond is a domain. With that in mind, let's go look. So, guys, looking at this atom, we've got a domain here, we've got one there, we've got one there, we've got one there. How many domains do we have? 4. The question is, so what? And you're going to find out in a minute that if you've got an atom with 4 domains and they're all involved in bonding, it actually looks like this. So guys, this carbon right here actually has this structure. There's other stuff hanging off the side, but that's what that guy looks like. Now, let's do this one. Guys, this one's a little trickier. Please talk to the person next to you about how many domains that guy has. Again, if you don't agree, chat about why you're different. You guys okay? So, Claire, I like the way you said that, but let me lead you to it. So, guys, here we go. We understand, well, let me ask it differently. How many bonds are on this carbon? Well, there's 4. We've got 1, 2, 3, 4. That's the octet rule, right? So guys, there's 4 bonds, but there are not 4 domains. So guys, this is a domain, this is a domain. But Claire, what did you say about this guy? It only counts as one domain. Guys, in the same way that if there's 4 antelopes on the prairie, it's still one domain. Guys, we've got a double bond right here, but it still only counts as one domain. So it's 3. Questions about that? Okay, now let's throw you another curveball. Guys, this oxygen. Chat with the person next to you about how many domains. Now I'm hearing different answers. Keep talking, you guys. So guys, let's talk, because now we have a new type of domain. This one was all bonds, this one was all bonds, now we've got unbonded electrons. So Claire helped us establish that this is one domain for the carbon. It's also one domain for the oxygen. But then what about these? Those are also domains. We find some electrons here, we find some here, so we have 1, 2, 3 domains. Questions on that one? You okay? Last one. Guys, this oxygen... oh, wait, did I do the wrong one? Shoot. I already gave that one away. My bad. So, guys, this one's 3. I'm sorry, I was looking at the wrong one. How many here? 4. 1 and 2, those are your bonding domains, and then 3 and 4. And so this would be 4 domains, which makes that one a lot less exciting because I just told you the answer. Sorry. Do you guys understand domains? Are you okay? Does that sit okay with you? All right. So guys, now that we know what domains are, we're ready to move on to idea number 2, and it's this. It's called the Vesper Theory. And guys, not surprisingly, Vesper is an acronym, and it actually stands for this. It is the valence shell electron pair repulsion theory. And guys, as you're writing down those words, if you're being more than just a secretary that is just blindly writing things down, guys, if you've got your chemistry hat placed on your head, you should be writing down those words and you should be thinking, oh, that makes sense. Or maybe you're thinking, duh. Or maybe you're thinking, oh, kind of already knew that. But guys, if you're not thinking those thoughts, we need to tear these words apart. So guys, let's talk about it. So valence shell electron pair repulsion theory. So valence shell electron pairs. Those are the domains. Guys, these are the places we find electrons. These valence shell electron pairs are the domains. But what do they do to each other? They repel. Why do they repel? What's their charge? Guys, they're all negative. All of these domains contain electrons, and these electrons, you already know, push on each other. Guys, that's also the reason, where's a good place to look? That's also the reason that the p orbitals are 90 degrees to each other. Remember, they repel and get away from each other? Well, guys, so did the domains. So all of this means is that electron domains repel each other. They get as far apart as they can. You want to include that in your notes. So guys, the Vesper theory simply says that these domains repel each other. So then the question becomes, so what? And guys, only write down the part that's underlined. What that means is these domains are getting as far apart from each other as they possibly can. And that's what gives them their really interesting three-dimensional shapes. So guys, reviewing as you're writing, here's what we know. We now know what electron domains are. They're the spaces that the electrons occupy around the nucleus. Bond, unbonded pair, single bond, triple bond, double bond, triple bond, it's all one domain. And now, guys, we know that these domains push on each other and they spread out. So guys, how you doing? Are you 2 for 2? So we know what domains are, and we know how they interact with each other. We got one more thing to do, and then we're going to flip this over, and we're going to start talking three-dimensional shapes. So you guys ready to flip, well, to go down to the bottom? Guys, the last thing is this, and there is not room for you to write this down, but just hear this out. So guys, electron domains do not all have the same size and shape. You're going to find out that bonded electron domains, and this is in your notes, guys, bonded electron domains are long and skinny. Why are they long and skinny? Guys, they're long and skinny due to the pull of two nuclei. They're involved in a bond. One of the nuclei goes mine, and the other one goes mine, and they pull and they stretch. And so, guys, bonded domains are long and skinny. So what does long and skinny look like in the world of electron domains? If you want to draw it, you can. Guys, this is long and skinny. I know it doesn't really look very skinny, but compared to a non-bonding domain, this is long and skinny. So guys, if you want a visual reference, probably off to the right would be the best place. You could draw this if you choose. So guys, that's long and skinny. You guys okay? So guys, let's then talk about non-bonding domains. So guys, non-bonding domains are short and fat. And I'll leave the lights off just to let you see this image, and then we'll turn them back on. So guys, non-bonding domains are short and fat. Why? Because they only have one nucleus pulling on them. And guys, because we only have one nucleus pulling on them, they get pulled down and they get short and fat. So guys, this is sort of by comparison what a non-bonding electron domain looks like. They are short and fat. All right. So guys, we are now done with the front of this page. We have established all the foundational stuff that we need. We know what a domain is. We know how they interact with each other. And now we understand that the bonding domains are long and thin and the non-bonding domains are short and fat. So guys, what I'd like to do to wrap this up with you is to show you an image of what this might look like. And then guys, at that point, we're going to turn this over on the back and we're going to look at the organization that Calvin talked about. And we're going to look at 4 domains, 3 domains, 2 domains, and talk about what these molecules actually look like. But guys, before we do, let's talk about sort of a real world example of what this might look like. So guys, it goes like this, and you've drawn this many, many times. It's a water molecule. Now guys, when we think about a water molecule, we know that a water molecule looks like this. But guys, what's missing from this model? What is not represented in this model? The unbonded domains. So guys, do you see this gray stick, and do you see that it's long and skinny? And this one, and it's long and skinny. But guys, what we're now going to do is we're going to bring these guys into the picture. And you're going to find out, you now know that there are 2 domains that are not bonding, and they are short and fat. And so guys, when we look at it that way, we understand that these domains are long and skinny. Those are the bonds. But then we've got 2 domains that are short and fat. And guys, these unbonded domains push these things down. Short and fat, Vesper theory, pushes these down and it changes the angle, and that's what we're going to talk about for the rest of the day. So, you guys, anything on the front that you want to chat about, clarify? You feeling okay? Are we good? All right, guys, let's flip it over. Here we go. All right, so guys, to get started, I have a question for you. Please do not write it down, but guys, let's talk about the answer. So I'm going to paraphrase. It says something like this. When 4 objects in 3-dimensional space spread themselves out as much as they possibly can, guys, what angles do they form? So first of all, let's make the connection to what we're actually, how does this connect to what we're learning? Well, guys, first of all, our four objects are the domains. Then this. How do we know that they spread out as far as they possibly can? Guys, that's Vesper Theory. They spread out. So the question is, when four domains spread out in three-dimensional space, what angles do they take on? So guys, you ready? This is a visual of what we're talking about. Here's our central point. And then we're going to go 1, 2, 3, 4 points. And they are as spread out as they possibly can. And when we connect the dots, guys, what are all four of those angles? Come on, you've done a little geometry. What are those angles? 90 degrees. Yeah, you guys know that much geometry, right? Guys, all four of those angles are 90-degree angles. So I got a question for you. Why is that not the answer to the question? Talk to the person next to you. Guys, why is the answer to this question, four objects spread out, why is the answer not 90 degrees? Talk about it. Landon, can I call you up to active duty in just a minute? I'm going to have you help me with something. Is that okay? It's pretty straightforward. So guys, I think we can probably take the answer to this and we can narrow it down to a really simple statement. Guys, why is the answer to this question not 90 degrees? What'd you talk about? What's missing? Why is the answer not 90 degrees? What's wrong with our picture? It's two-dimensional. Guys, in two-dimensional space, those would be 90-degree angles. But guys, we do not live in a two-dimensional world. We live in a three-dimensional world. And as a result, guys, the answer is no longer 90 degrees. So here's my sadness that I need to share with you. I used to demonstrate the difference between 2 dimensions and 3 dimensions with this. But guys, I can't get it to work. Maybe it'll work today. Let's see. So guys, first of all, let's talk about what we got here. So what does this shape have to do with the question? Well, guys, can you see the 4 points in three-dimensional space? Those are the corners of the pyramid. And so the central point is in the middle. So the other thing is this. How did I build this so that I know that all 4 of these points are as far apart as they can get? I cut the straws all the same length. Guys, it doesn't matter how long they are. If they're the same length, they're as far apart as possible. This is where things get sad. Apparently my bubble, this is just bubble juice that you can buy by the gallon at Walmart. And guys, oh, okay, this might actually work. Crap. Come on. Oh, it worked. Can you see it? Oh, shoot. Guys, this is the first time this has worked. Oh, darn it. This is the first time this has worked all year. It didn't work again. I think my bubble juice is just old. But let's try one more time. Come on. You want to work. Did you see it that first time for... Oh, there. Oh, no. Have I cussed yet? I feel like I'm about to. I need to be careful. Darn you. I want it to work so bad because it's cool. Now it broke. All right, I'm not doing well. Guys, this seriously may not work, in which case Landon and I have got to back up. But yeah, I just don't think it's going to work. I just need to go to Walmart and buy more bubble juice. Yeah, sorry, guys. Oh, dang it. Did you see it there for a moment?
Yeah.
Just say yes so it makes me feel better. Oh, there. I'm just going to do this for an hour. I hope you guys don't mind. There. Do you see it? I'm going to look this way so I don't... Popped again. But guys, you saw the angles, right? So this has always worked. And then I did it first period yesterday and it didn't work. And so I had to mad punt in the middle of class. And when I did, and I'm going to have Landon help me with this. Stay put, I'll come to you. Guys, what I ended up having to do was show another representation of the idea that these are not 90-degree angles. So you got to fall back on your good friend party balloons. So guys, now what we've got is this. Same idea, we've got four things spread out in three-dimensional space. The reason I don't prefer this is because it's hard to see the 90-degree angles. Grab a ruler. So we're going to, Landon and I together are going to try to show you this. So if you could take that blue ruler and could you just hold it like that, and you want to cut the middle of the balloon and then just sort of stop in the middle. Do you see what I'm saying? Yeah, just like that. And then, so guys, what Landon has done is he has bisected this balloon. And then if I come down here and, let me do it. Sorry. Guys, if I come down here and bisect this balloon, can you see that those angles are not 90-degree angles? Are they bigger or smaller than 90 degrees? Can you see that they're bigger? Landon, thank you. Again, it's not the best way to do this, but it's the best we can do right now. But guys, the bottom line is if you can see that, you can see that these are bigger than 90-degree angles. So what are the angles? And you need to write this down in your notes. Guys, the angles are actually 109.5-degree angles. And now, guys, we've got to give this structure a name. So now, guys, let's turn to a plastic ball and stick model. So you guys can see the 109.5-degree angles right there. But now we need to name this. And guys, from geometry, and I know your background's not good, but from geometry, the prefix for 3 is tri, right? Trigonal, triangle, that sort of stuff. Guys, do you know the prefix for 4 that isn't quad? There's another prefix for 4. Any of you know it? They don't teach you this stuff anymore, do they? Guys, it's tetra. 4 is tetra. And so, guys, the name for this shape is tetrahedral. All right. So, guys, with that said, let's go down here to our table. And guys, I'm going to give you a huge head start on this. Guys, these 4 molecules have something in common. But before we can talk about it, let's draw them. And so, guys, put all of these in your notes. CH4, NH3, H2O, and HF. And then, guys, draw their Lewis dot structures. The reason that I'm giving you these Lewis dot structures rather than having you draw them is because you've already drawn them. Guys, you've seen all of these in previous, in assignments 3 and 4. So you've done all of these. So there's no sense in having you do them again. Now, guys, as you're wrapping these up, I have 2 questions that I need you to be able to answer. Guys, question number 1 is this. What do they all have in common? And then question number 2 is this. Why are they in the order from top to bottom that we're placing them? So guys, again, as you're wrapping up what you're writing, 1, what do they have in common? And 2, what's the pattern top to bottom? So guys, chat with the person next to you. What do they have in common? What's the pattern? Roman, you're on it. So guys, a couple more seconds and we'll pull it together. Love it. So guys, let's do the first question first. What do they all have in common? They all have 4 domains. Guys, they all have 4 domains. Here we've got 1, 2, 3. They all have hydrogen. 1, 2, 3, 4 domains. 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 So guys, the central atom all have 4 domains. Now, Roman, what's about the order? Good for you. I love this. So you're looking at the lone pairs. None, 1, 2, and 3, right? But as they are gaining lone pairs, what are they losing? Bonds. 4, 3, 2, and 1. And it doesn't matter which one you're looking at. What we've got is, as we go down, more lone pairs and less bonds. But guys, what about this? What are the bonds, what do the number of bonds in lone pairs always add up to? 4. Right? The first one is 4 and 0. Then it's 3 and 1, 2 and 2, and then 1 and 3. Guys, they always add up to 4. But you'll notice if you zoom out with me, guys, that 4 is this 4. They all have 4 electron domains. And as Roman pointed out, the number of unbonded domains go up as the number of bonding domains go down. Do you see all these interesting patterns? So now, guys, we're going to talk about it by working our way from left to right. So, guys, on CH4, how many bonding domains are there? 1, 2, 3, 4. There's 4 bonding domains. How many non-bonding domains are there? 0. And guys, the molecule looks like this. But guys, you already know the name of this. What is the name of this structure? You wrote it down earlier. Look up. What's the name? Tetrahedral. And what are the angles? Boom, you're done. Guys, the angles are 109.5 and this structure is tetrahedral. So now you're thinking to yourself, well, yeah, kind of knew that. 4 domains, tetrahedral. But guys, what you're going to find out is that none of the rest of these is this true. Now let's do NH3. Guys, how many bonding domains are on NH3? 3. How many lone pairs? 1. Now guys, watch. This sure as heck is not tetrahedral. This does not look like this. So guys, let's talk about why. What's going on? Well guys, the difference is this. One of the domains on NH3 is not bonding. But realize this is a cloud of electrons, so we really can't see it. So guys, the molecule looks like this. But now guys, watch my fingers really close. So what do we know about the bonding domains? Long and thin. What do we know about the non-bonding domains? Short and fat. And short and fat, watch my fingers, short and fat pushes down on the long and skinny. And guys, does this angle get bigger or smaller? Smaller than what? Where did it start? 109.5, and then the unbonded domain makes this angle smaller, so the angle, that's not turned on. Guys, the angle is less than 109.5. That's all you need to, guys, you don't need to know this. The angle is actually 107. You just need to know less than 109.5. So guys, ready? Now we need to name this. What is the geometry word for 3? Try. But guys, would you buy this if you look? That it looks like a pyramid? Huh? So the name of this is trigonal pyramid. All right, guys, let's keep going with the pattern. So looking at a water molecule, how many bonding domains? 2. How many non-bonding domains? Also 2. And guys, the molecule looks like this. This is a water molecule, but what's missing? The unbonded pairs of electrons. And again, guys, what do these unbonded pairs of these short fat guys do? Push these down. And what does that angle become? Smaller than 109.5. It's actually even smaller. You don't need to know the number, but it's smaller than 109.5. But now, guys, you ready? We got to name this thing. Thoughts? You're going to be really disappointed. Guys, sadly, when they named the shape of this molecule, they just called it bent. Makes sense, though, because it's bent. But that's what we got. All right, so now, guys, we've got one more to go. HF. The fluorine only has one bond. As Roman pointed out, we then have a maximized number of unbonded pairs, and that would be 3. And guys, the molecule looks like this. So this is HF. But guys, do you realize there's 3 unbonded pairs on the other side? But guys, watch close before you talk. What is the angle in this molecule? There isn't one. Did you learn in math that 2 points do not define an angle? What do 2 points define? You guys not learn this stuff in math? They define a line. Guys, 2 points can't define an angle. 2 points can only define a line. So there is no angle, so we call it undefined. And guys, the name that we give this structure is what we call straight. So guys, there you have it. We understand domains, we understand their structures, we understand how the bonded and non-bonded domains change the shape of the molecules. And guys, fundamentally, don't write this down, here's what we know. What do all these molecules have in common? 4 domains. But guys, what is it that determines their structures? Their molecular geometries, and the answer is the number of domains that are bonding and the number that are not bonding, again, depending on how you look at it. Questions or thoughts on this? You okay? So guys, we are going to wrap up the rest of this pretty quickly. You now understand the patterns. You now understand the logic. What we need to do now is we need to talk about 3 domain structures and 2 domain structures. So guys, let's talk about 3 domain structures. Again, you're not writing this down, but the question is this. We now have 3 domains spread out in 3-dimensional space, and they're as far apart as each other as they possibly can get. And so guys, it looks like this. 1, 2, 3 things spread around the central atom, and we connect these with lines. Please tell me you know this angle. So guys, a whole circle is 360 degrees. 360 divided by 3, they're 120 degree angles. But hold on. Guys, what about in 3-dimensional space? And this is a place where the balloons are actually really cool. Can you see the 120 degree angles? But guys, here's the thing that's neat. If we think about this in 3-dimensional space, here's what happens. If this balloon tries to move up or down, the other balloons move with them. But that's 2-dimensional. What if we move forward and back? And guys, the answer is if we move forward and back, the other balloons move with them as well. And even in 3-dimensional space, the answer is still 120 degrees. All right, so now guys, we've got to name this thing. And we already know that 3 points is a triangle. But guys, check this out. Here's the difference. You have seen trigonal planar or trigonal pyramid that looks like this. Guys, this is what we call trigonal planar because it's flat and it's all in the same plane. So this is what is called trigonal planar. All right, so here we go. Guys, as your eye is now naturally dropping down to the table where we're going to organize this information, some of you are maybe thinking to yourself, if 4 domains had 4 boxes, 4 rows, why does 3 domains only have 2? And guys, you're going to find out the answer is it should have 3. We're just not going to include the last one, and you'll see why in a minute. So guys, these are going to be our examples. CH2O and NO2 with the -1 charge. Guys, they look like this. Get them in your notes. Guys, okay? So maybe the same questions. What do they all have in common? 3 domains. Here we have 1, 2, 3. Here we have 1, 2, 3. So guys, they both have 3 domains around the central atom. But then what order are they in? The same order. Guys, here we've got 3 domains that are bonding. You like, Roman, to look at the unbonded. Here we've got 1 unbonded domain and 2 that are still bonding. So they're also in order top to bottom by the number of bonding domains. So guys, with that in mind, let's look at the top one. This has got 3 bonding domains, a single bond, and a double bond. How many unbonded domains are on this? Guys, we only look at the central atom. We don't count these at the top. So around the central atom, we have no non-bonding domains. It's only the central atom. But guys, this is it. This I don't know if you know this. This is actually formaldehyde, the stuff that biology teachers soak dead stuff in so they don't rot. Guys, this is what this molecule looks like. Double bonds, single bonds. Guys, can you see the 120-degree angles? And can you see that it's flat? Guys, that's it. The angles are 120 and the geometry is trigonal planar. All right, so you guys know where this is going because you're following the pattern. So looking at the one down below this, guys, now we have 2 bonding domains. We've got a double bond and a single bond, so we have 2 bonding domains, and now we have 1 non-bonding domain. And so guys, the idea is that the molecule looks like this. You've got a double bond to one of the oxygens and a single bond to the other. But again, guys, what's missing? We're missing the unbonded pair of electrons up top, and that unbonded pair of electrons pushes these down and makes the angle smaller than what? Not smaller than 109.5, smaller than 120. So guys, this angle is smaller than 120. So now guys, we got to name it, and you already know the name. Looking at the molecule, what's it look like? It's bent again. Guys, the molecule is bent. So at this point, it always brings up sort of an interesting question. And the question is this: why did we not put another row down here where we talk about a molecule that has 1 bonding domain and 2 non-bonding domains? And guys, the reason we didn't do that is because we don't need to. Because anytime we have 1 bond, we have 2 points. And anytime we have 1 bond and 2 points, do we have an angle? No. So the angle will be undefined, and the name of this will also be straight. So guys, anytime you have 1 bonding domain, it's always undefined and straight. We good? All right, guys, we got about 3 more minutes. Let's wrap this up. So we got to go here, and we got to go back, and we got to do this. All right, guys, Last question. Two things, three-dimensional space, all spread out. 1, 2, what's the angle now? 180 degrees. And guys, these things are all in a line, so we call this linear, or we actually pronounce it linear. Now guys, we're only going to look at one example, so let's do that now. The one example we're going to look at is carbon dioxide, which looks like this. Dun, dun, dun. So guys, you know the drill. Looking at carbon dioxide, how many bonding domains are on the carbon? Well, there's two. We've got a double bond in one direction, we've got a double bond in the other direction. So guys, we have two bonding domains. How many of these domains are not bonding? None of them. Yeah, we've got non-bonded domains on the oxygens, but we're only looking at the central carbon. So guys, the molecule actually does look like this. You have actually got double bonds that are 90 degrees out of phase with each other. In AP, well, next year we talk, this is actually really cool. There's a lot of stuff going on here simply because these bonds are out of phase. It's actually kind of how vision works, but it's a whole nother story. But, so guys, this is what the molecule looks like. But can you see that these are all in a line, and can you see the 180 degree angle? Guys, that's it. The angle is 180 and the geometry is linear. Again, we did not do the example of one bonding and one non-bonding because, guys, that would simply be undefined and straight. So, guys, there you have it. The question is, what are we going to do with this? The answer is this. Guys, grab your activity. This is what we're going to do with this. This is your homework for tonight. So guys, what you're going to do, and this is not on your paper. I don't know if I told you about this. This activity that you guys have in front of you, Miss Call and I actually made this up right before Christmas. And we liked it so much that it's actually radically changed the way we teach all of this molecular structure stuff. And it's a lot better. But guys, this is what you are going to do on your paper. In this box, you are going to write DG for domain geometry off to the left, MG for molecular geometry, and then put a little angle symbol. So DG, MG, and angle. And then, guys, this. You are going to look at the Lewis dot structure, and you're going to ask yourself this question. How many domains are on the carbon? 4. So what is the domain geometry? And that would be tetrahedral, because, guys, looking at your top chart, and you're going to want your notes out while you do this. Guys, looking at the top chart, 4 domains is a tetrahedral domain geometry. So now, guys, the next question that you ask yourself is this. How many of those 4 domains are bonding domains? How many of those domains are bonding? And guys, it is 4, but there's a better way to think of it. The better way to think of it is this. All of them. Because, guys, something magic happens when all your domains are bonding domains. To represent it, we're just going to do this. Draw an arrow down. Guys, when all of your domains are bonding domains, the domain and molecular geometries are the same. Then, guys, what's the angle? Well, the angle is 109.5. Does it have a less than symbol in front of it? Doesn't. Guys, how do you know? And gang, the answer is this. Again, we're looking for patterns. If the domain and molecular geometries are the same because all of the domains are bonding, then the angles are the pure angles, and it'll be 109.5 without the less than in front, because it doesn't have any non-bonding domains to muck up the structure. Questions? Yeah, Keith. So, domain geometry, molecular geometry, and angle. Is that okay? Let's do another one. Is that okay?
What's the down arrow?
Okay. So the down arrow means that the domain geometry and the molecular geometries are the same. So instead of writing it twice, we just draw an arrow. Is that okay? All right. So guys, dig deeper into your packet. I think it's on the second page. Oops. Yeah, on the second page, guys, take a look at these. We're going to do two of these together. We're going to do the first and the fourth. So guys, do you see where CH3OH is in your packet? You okay? So guys, here's what we're going to do. We are going to call the oxygen the central atom. If you're not sure which ones are central, look on the homework answers, and we've underlined them on there. But guys, we are going to call the oxygen the central atom. So guys, we are looking at this oxygen. So guys, same deal. How many domains are on the oxygen? 4. 2 bonds, 2 non-bonded. So guys, we've got 4 domains. So the DG, the domain geometry, is tetrahedral because it's got 4 domains. Now guys, we need to know the molecular geometry. So now we need to ask ourselves, how many of those domains are bonding? 2. So guys, if it's helpful, look on your table. Here are the tetrahedral domain geometries. And then this has got 4 bonding domains, 3 bonding domains, 2 bonding domains. And when you get to 2 bonding domains, guys, what is the name of that molecular shape? Bent. And then, what is the angle if it's bent? Well, guys, it starts at 109.5, but does it stay 109.5? It becomes less than 109.5 because of the unbonded electrons. So guys, now, and you're going to need to go back and redo this for number 1 in a minute, there's one more step to your homework assignment. You need to draw an arrow from here over to the atom that you are calling the central atom. So guys, why are we having you draw that arrow? Well, check it out. Guys, if you look at this, do you see that this is bent? Guys, that's the point. That oxygen has a bent structure because of all the things we just identified as true. So gang, let's go down and do the last one on this, well, the 4th one down on this page, and then we're going to turn you loose. So guys, down here we've got this carbon atom right here. And again, we need domain geometry, molecular geometry, and we need the angle. So guys, looking at that carbon, how many domains does that carbon have? How many domains, y'all? You see 3? We've got a single bond, and a double bond. That's 3 domains. So guys, that means the domain geometry is trigonal planar. And guys, you're welcome to abbreviate, but don't put TP because that could also be trigonal or pyramid. You need enough that you can tell the difference. So guys, that is trigonal planar. Now, you now need to ask yourself, how many of those domains are bonding domains? How many are bonding domains? all of them. And guys, because all of them are bonding, the molecular geometry is the same. You can just draw a down arrow. They are the same. So now, guys, what's the angle? Well, the angle is 120. But is the angle less than 120? No. Why not? Because there aren't any unbonded electrons on the atom. See how this all fits together? But guys, then this. The last thing you're going to do is you are going to draw an arrow to the carbon that we're talking about, and it's the carbon that's double bonded to the oxygen. So guys, we are talking about that carbon right here. You need to find it in your model. But guys, check this out, and you don't need to do this. But if you draw in the lines, you can see that this is trigonal planar, and all the angles are 120 degrees. So guys, we've got about 15 minutes left. We're going to skip the pledge. You should maybe get done with this today. But guys, here's what's going to happen. When I see you on Monday, we are going to go over all of your names and angles, and we're going to record that as a homework assignment. Then you're going to turn this into me, and that is going to be counted as an activity. And then guys, on Monday, we're going to do a lab where you're going to build all these models, and then Wednesday will be the test. You guys good? Let me print the answers for you so you have them on the wall. Guys, you're welcome to work with those around you. But guys, turn back to page 1 and let's get cooking on these and see how much we can get done. All right.